Hi guys, we are working with the mole-to-mole ratio today. We are finally starting our stoichiometry unit. So I know that for some of the classes, the page number isn't 25. It's actually a little bit lower than that, but or like smaller than that. But we're going to go ahead and use page 25 for this first page of stoichiometry so that we can kind of keep it consistent. And then keep your notebook up to date. I think right now it is especially important to be keeping your notebook up to date and keeping it like accurate and keeping it as a tool for you as we're moving forward. So the first thing that I would do here is make sure that under the box for M, you write mole-to-mole ratio and you write page 25. We are going to have a quiz that is specifically over the mole-to-mole ratio. So this would be a really good study tool and help page for you as we move into that. So go ahead and then get to your page 25. I anticipate that during this little video thing, you're going to end up having to pause, write things down. The good thing is you can go back, like, what did she say? Where did she get this number? You can navigate through the video at your own pace. So I'm just going to kind of like talk. I'll go a little bit quick so that the video isn't super duper long. But please definitely make sure you're pausing, you're going back, you're listening to everything I have to say and doing the practices along with me. Engaging in the practices, how you're going to actually like learn how to do this. So the mole-to-mole ratio is how we are starting stoichiometry. So I've said this word 100 times probably already, but you really haven't learned what it means. And even though the definition here just says Greek for to measure, what I want you to think about is it does have to do so much with measurements. Stoichiometry is basically like cooking in a kitchen. It's going to tell you how many ingredients you need and how many products you're going to get out. And we're going to use that basic balanced chemical reaction to help us determine now how many grams of things do we need, how many liters of things do we need, and how many grams can I expect as an output, and how many liters can I expect as an output. So we're kind of combining our skills with mole conversions and with balanced chemical equations to now look at more accurate measurements of a chemical reaction. So the procedure that we're going to do is critical right here. This is something that I am going to have you come back to all the time. Kind of like I always have that mole roadmap up on our board. We're going to always have this mole-to-mole ratio roadmap up on our like reference as we are moving through the next few weeks. So what you can see here is I am now concerned not only with going from grams to moles, liters to moles, but I need to go from moles of a substance in a chemical reaction, which I'm going to call A, to moles of another substance in that chemical reaction, which I'm going to call B. Okay, those are just generic, these are just generic variables for whatever chemical we're talking about, right? How am I going to get from, for example, what if I'm talking about moles of water and I need to get to moles of oxygen, or I'm talking about moles of hydrogen and I need to get to moles of hydrogen peroxide, whatever it is, it's a different thing in your chemical reaction. The way that you're going to get there is you're going to use what we're talking about today, which is the mole-to-mole ratio. Okay, so what does the mole-to-mole ratio look like? Well, this is irksome that it does this. Okay, the mole-to-mole ratio is based on coefficients from the balanced chemical equation. And I'm using green here, and you can definitely tell that probably what I'm going to do is when I do the math, I'm going to continue to use green where I'm using mole-to-mole ratios, okay? Where am I going to get those mole-to-mole ratios? I'm going to look at the coefficients from the balanced chemical equation, okay? So now you can see probably what I'm going to do is I'm going to convert grams to moles or liters to moles, and I should know that to go from grams to moles, I use molar mass. To go from liters to moles, I use 22.4. Then I'm going to use the mole-to-mole ratio, which are the coefficients, to get to my other substance. And then I can use those same conversion factors to get me out to the other unit that I want. Okay, so let's start with an example. So this is the chemical equation, and this is just lower down in your page. I just can't fit it all on one screen, guys. Okay, so write down, you've got nitrogen and hydrogen yields ammonia. Okay, so this chemical reaction, I already had to balance. All right, to balance it properly, you would just say 1 here, you would say 3 here, and you would say 2 here. Okay, so when we're balancing our chemical equation, we're actually saying this chemical reaction occurs when 1 mole of nitrogen and 3 moles of hydrogen combine, and it will create 2 moles of ammonia. Okay, that should have been something that you saw at the atomic level yesterday as you were balancing the chemical reaction. You had to like add in hydrogen molecules, and then you had to add in an ammonia molecule. So yes, it's true at the molecular level if we're talking about single molecules. But on a wider scale, we're also talking about it in terms of moles as well. Okay, so we would start off with this balanced chemical equation, and we would start off understanding that the exact combination we need for this chemical reaction is 1 mole nitrogen, 3 moles hydrogen, 2 moles ammonia. Okay, so what kind of problem would we get? Well, it would ask us something like this: how many moles of hydrogen are needed to react with 2 moles of nitrogen? Okay, so what I'm going to continue to do, especially because now we're not talking moles, grams, which we will be. We're not just talking about the same substance. We're talking about moles of nitrogen and moles of hydrogen. So just like I did before, I'm kind of like boxing the information that's given to me in the problem. I know my problem wants me to start at 2 moles of nitrogen. So as you can imagine, that's going to be the very first step of my conversion here. And then it wants me to go to moles of hydrogen. So I know I need to get from here to here. And the way that I go from one substance to another substance is using the mole-to-mole ratio, which are the coefficients from the balanced chemical equation. Okay? So mole-to-mole ratio problems are one-step problems. And I highly, highly, highly recommend that you start doing it like this, because we're going to start adding more steps to the left and to the right of these one-step problems, because I'm giving you moles and I'm asking for moles, but in the future, I'm going to give you grams, ask for grams, give you liters, ask for liters. Okay? So again, I have boxed this piece of information, 2 moles of nitrogen. So the information that I start with, obviously, is going to go, oops, why did this disappear? Oops, it never disappears. Okay, so this 2 moles of nitrogen goes here, guys. Okay, 2 moles nitrogen, 2 moles nitrogen. You're going to put it right here. All right. The important thing to do is what we have been doing for a really long time, which is whatever unit you're given, what goes up must come down. Okay, so that's why this right here is moles nitrogen. Okay, then you put the unit desired up at the top. Well, the unit that I desire is moles of hydrogen. So I'm going to put moles of hydrogen here at the top. All right. So what we need to do now is we need to fill in these numbers. Okay. Before, when we were doing our mole conversions, we would always say, well, wherever mole goes, 1 goes. And that's true for a mole conversion, because we're using a conversion factor like 1 mole is 6.02 times 10 to the 23rd atoms. 1 mole is 22.4 liters. But when we're talking about a specific chemical reaction, and we're talking about 2 of the reagents, which is another word for a reactant or a product in a chemical reaction, we have to use the coefficients in the balanced chemical equation. So right here next to moles nitrogen, I am not going to put 1. Well, actually, I am actually, because the coefficient in the balanced chemical equation is 1, but I don't automatically put 1. I'm not just like 1 mole, 1 mole. Then what would be the point of this conversion factor? It would always just be 1. That's not always the case. It happens to be the case here because look, for 1 mole of nitrogen, we need 3 moles of hydrogen. So I kind of answered the next question in saying that, because I'm going to make that ratio be reflected in these steps. For 1 mole of nitrogen, I need 3 moles of hydrogen. So again, where did this 3 come from? It came from the balanced chemical equation. Okay, so again, you should have copied down on your notes 2 moles of nitrogen here. The box just doesn't disappear. So we would then just solve like we always do, and we're going to say 2 times 3 equals 6. Okay, so let's look at another reaction. So this is what I'm probably going to start giving you as part of your practices, because at this point you should, 1, be able to create formulas from names. 2, you should be able to balance chemical equations. And now 3, you're going to have to start doing some calculations with a balanced chemical equation. So potassium chlorate, we would say potassium K1 plus, chlorate is ClO3 minus, right? So I'm coming up with this formula here. Decomposes into potassium chloride and oxygen. So this is another compound I'm going to have to create. So we're going to say, oh, I'm sorry. First, I created this formula, 1 to 1, right? Then here we've got potassium is 1 plus, chlorine is 1 minus. So that will again be a 1 to 1 ratio. So the formula is going to be over here. It's going to be just KCl. Okay, so this is an easy one. And oxygen, what do we need to remember about oxygen when it's by itself in a chemical reaction? So 2, right? So you would start off with your skeleton equation. These are just the species or reagents that are involved. And then it is really important that I balance the chemical reaction, because this is going to give me my mole-to-mole ratio. So pause the video and balance. Should have come up with 2, 2, and 3. Okay, this is one we've done before, right? Okay, so the problem that I would give you next would be how many moles of oxygen are produced by 6 moles of potassium chlorate. Okay, so once again, what I've done here is I'm like, all right, I'm just going to box the information that I'm given. And notice specifically that I boxed the chemical formula as well, because I know I'm converting formulas now too, from species to species. So then I circled where they want me to go. They want me to go to moles of oxygen. So how many moles of oxygen is what they want, are produced by 6 moles of KClO3 is what I have. All right, so we start with what we have. And what we have is 6 moles KClO3. All right, and then just as we always have done, I'm going to say what goes up, this unit right here, must come down. So moles KClO3, moles KClO3. And notice that I wrote the whole thing. I know it's going to strain your wrist, but you have to write the whole thing, because now we're talking about switching units and switching which chemical we're talking about too. So it is important to write it both, so that you're setting up your problem correctly and you're getting the right answer ultimately. Okay. So what are the units I want to go to, or the units desired? Moles oxygen, right? So now I have it at least set up to where I have the right unit and substance in the right spot. Now what I need to do is get my conversion factor, which, remember, if I'm going from one species to another species, or one chemical to another chemical in a chemical reaction, I have to use the mole-to-mole ratio. Where do I get the mole-to-mole ratio? Where do I get that from? I get that from the balanced chemical equation. So I'm going to refer back up here to get the numbers that I need to put in here. All right, what number am I going to put where? Well, I like starting with the substance that I'm starting with. I think that makes sense. So KClO3, I would take a look back at the chemical equation and I would say, okay, the coefficient that's in front of KClO3 is 2. So I put a 2 in front of KClO3 in my conversion factor, right? Then what is the next substance? It's oxygen. So I take a look at oxygen in my chemical equation. And again, I see the number 3. So what do I put next to moles of oxygen in my conversion factor? I put the number 3. Okay, so it should be a simple math problem from there. All we're doing is multiplying across like we always do. And then we take whatever our top answer is and we divide by our bottom answer. So when I get my calculator out, I'm going to type 6 times 3. I get 18. And then I'm going to divide by 2. So it should be 9. Ultimately, my answer is 9 moles oxygen. Okay, obviously I'm giving you guys some real simple, straightforward examples to start with. The numbers are going to get more complicated as we continue in our practice, so make sure that you're getting these easy ones before we start moving on to more difficult ones, and you will ultimately take a quiz on this concept right here. Okay, so go ahead and go to your left side. You should be on 25A, and I'd like for you to copy this down, thinking pair share. You're copying down zinc and hydrochloric acid. Okay, so I'm asking you to do a lot here because I'm asking you to change zinc into a formula. I'm asking you to change hydrochloric acid into a formula. And then I'm asking you to actually predict the products of this chemical reaction, right? If you need to refer back to notes, you can. But I highly suggest you genuinely attempt this practice because this is what you're looking at doing very quickly here. So pause your video if you haven't. Okay, so you should have come up with zinc VN, hydrochloric acid, HCl, and then you should have remembered that hydrogen was the one that got kicked out, and it is H2 because it's part of Brinkelhoff. And then zinc chloride, if you made the formula correctly, should have been ZnCl2 because you should have crisscrossed those charges. From that, you should have just needed to put a 2 in front of hydrochloric acid. Okay, you should be at this point by now. If you have questions on this, please let me know so I can assist you. All right, now here comes your mole-to-mole ratio practice. I want you to answer, so copy down how many moles hydrogen, how many moles of the hydrogen, remember this is H2, it looks like it got covered up a little bit, are produced from 3.5 moles of HCl. So as you're copying this down and getting started, I might box this information and then potentially circle this information. So pause your video. And now you can check. Okay, first, we're putting moles HCl at the bottom. In my balanced chemical equation, there's a 2 in front of HCl. So I include that in my calculation. 1 mole of hydrogen. Okay, I put moles hydrogen at the top because it's what I desire. And there's 1 mole in my chemical reaction. Okay. And to solve this, you should have gotten 1.75 moles of HCl. This is your answer. This is perfectly acceptable if you are in general chemistry. Honors Chem, we should note that there were 2 sig figs in my problem. So there should be 2 sig figs in my answer. It should be 1.8 if you're rounding correctly. Okay? Go to Socrative, complete the practice, and actually read the feedback. I give you guys some explanation if you get the question wrong or if you get the question right to make sure you're doing this accurately. Okay, let me know if you guys have any questions. We will practice this again tomorrow, but there will be a quiz specifically about how to do these problems. Okay, thank you.